So this is going to be a little tricky today because we're going to try and do something a little different than what we've done before. Hi, my name is Simon Sponberg. I'm a faculty member here at Georgia Tech, and Ethan Wold is a graduate student here who's part of the IMSI Summer Institute. You might have heard him give a talk at one of the all-hands meetings recently. He is busily preparing the demo that we're going to do. Yes, we're going to try and do a demo over Zoom. We'll see how well this goes. Bear with us. We're going to try and do a couple of things today. What I want to do is go back a little bit to basics and look at how do we describe muscle function in a moving animal. And oops, this is the wrong side. What happened to my slides? Hold on. The wrong one. Give me just a second. So what we're going to try and do is, there we go. I had it on a different screen. Too many different screens going. Okay. You can see that now, yeah? Yes, that looks right.
Yes, we can see.
Good. All right. So in this workshop, what I want to do is you've gotten sort of an overview, especially in the first full workshop, workshop 2, about work loops and how they're sort of being used in modern contexts. But work loops are really tricky mathematical and empirical tools that we use to understand the function of muscles in realistic settings, in settings that simulate or are actually in vivo. And I want to talk about how do we get these kinds of data. I want to talk about how do we interpret these kinds of data and some of the subtleties in interpreting them, what a work loop is. And then we want to actually show you the collection of a work loop data set and some of the issues that go into actually collecting this kind of data. Because it's very easy to say, oh, we've got force, we've got length, we're going to plot them against each other, and we're going to get work out of that somehow. Actually, the way that people usually do that is mathematically not quite right. And we'll go through that a little bit. And then we will actually look at empirically how we do this. And then we've got some data that you all will be able to actually try to plot your own work loops from our data, and we'll have you try and interpret it a little bit. So this is going to be, the first 30 minutes is going to be actually a whiteboard, a virtual whiteboard. I'm going to do this with sketches instead of slides because I think it's a little easier to understand. And then we're going to go over, I'm going to give you a few slides that sort of orient you to the experiment. And then we're going to go over and actually watch Ethan run an experiment for about 20 minutes and collect some work loop data. And then we'll do the magic cooking show thing, right? Where they put it in one oven and they pull it out done from the other oven. We have some prepared work loop data that we will send, that we've already sent you, and that's online. And you can pull that down. And for the last 30 minutes, your task will be to try and plot that data in whatever program you want to use and figure out, we've given you data for 3 different work loops. And we want to know which one of those work loops is a motor, which one's a brake, and which one is doing net zero work. And so that's what we hope to get out of this. All right. Here we go. So I think it's really useful to go back to real sort of fundamentals of thinking about muscle. And so I'm going to beg your forgiveness with my drawing capabilities, and I'm going to do this on my iPad. Okay. So I want you to think about, I'll make sure that that's coming up. Okay, good. All right. So let's take a muscle, and I want you to think about what's happening if you've got a muscle that is, we're trying to characterize the function of. And for this, let's take the muscle. I'm going to do one quick thing. Nobody needs to look at me from multiple views as I'm doing this. We're going to take a muscle, and what we're going to try and do is characterize its function. So what do we mean by that? Okay, let's say we took a muscle out of an animal and we plotted and we prepared it here. And so here's my sketch of a muscle coming in. And usually when we take a muscle out of an animal and do an in prep, we fix one end of it. Now, this could be grabbing on to the end of the muscle. It could be, if the muscle is attached to an exoskeleton, it could be fixing that part of the exoskeleton. You'll see how we do this in the future. I'm taking a few liberties with how I've drawn this. You could also do this inside an animal, where we think of, like, if we took a muscle and we had a tendon buckle on it or something. We're measuring force at one end. But we're going to have a measurement over here where we're going to be measuring the force that the muscle produces. Yeah. If we take the muscle out now, we might then have it set to some length, like its operating length or its resting length. I'll not. Okay. And so we usually think about the sort of, we have a length axis, L, and we have a force axis, F. All right. So how would we typically characterize this kind of muscle? Well, if we wanted to do it in a static context or in a traditional context, one of the first things that we might do is we might do a twitch response. We might say, okay, we've got a neuron that's coming in and innervating this muscle. We're going to grab onto that neuron and we're going to create a nice little lightning bolt of activation and stimulate it. That's my best lightning bolt, okay? And that can be done through the nerve. It could also be done through extracellular electrodes. That's how we'll actually do it later. And you might look at the force response over time to a twitch where the force would be at 0 at rest, and then we stimulate it with a single motor action potential or a single burst of activity. And we look at the force rise. When we do these experiments, when you do a twitch response, what you normally do is you fix the muscle at a certain length and you measure the force output from it. And you usually, when it's formally a twitch response, you're doing it usually to just a single pulse of activation. Now you could do this to multiple pulses of activation. We could add 2 spikes, right? Boom, boom. And we might get a larger amount of force that decays slower. And we could do that all the way up to tetanus, okay? Which is the maximum activation that a muscle could have. That's one way that we would characterize a muscle. Another way that we would characterize a muscle is we would do a force length curve. And you already have seen this before, but I just want to talk a little bit about technically what you're doing in an experiment when you're usually doing this, right? Is you're not activating the muscle and pulling it to different lengths. That's not how you're getting this force length curve. When we talk about a traditional force length or length tension curve, tension is just force in the axial direction. That's why you'll hear both. You'll hear length tension and force length. When we're doing this, when we talk about the classic force length curve, what you're actually doing is you're doing a bunch of maximal responses at different lengths. And so you're holding the muscle at a length. And then you're doing usually a tetanized response at that length to measure the maximum force. So you're actually getting a series of points along here that are each separate empirical measurements. But then we oftentimes draw it as a curve that's related to the sliding filament theory for muscle. I thought about going through that. I don't really have time to go through why we expect the force length curve to be this way. If that's not stuff that you've had before, don't worry about it too much right now. But for those of you who have seen it before based on the actin and myosin, you sort of expect there to be roughly 4 phases in this force length curve. And what I've drawn here actually is the active force length curve. And there'll also be a passive force from the muscle that typically goes up like this. Passive, active. And so the actual empirical curve that you might measure would be looking actually something like a combination of the two, which would look something like this. And what I really want to emphasize with these force length measurements is that when people do them, it is not like they're dynamically changing the length. They're fixing the length at a specific length and asking how much force can I get out of the muscle at this length? And then they're doing it at another length and measuring the force. We call this a quasi-static or a steady measurement, quasi-static or steady measurement, because it's steady at a fixed condition, a fixed length. We measure the force. Then we go to another one, we activate again, go to measure another force. It's really important because you want to be very careful interpreting these force length curves as when a length changes, because they're actually individual static measurements. And they're usually measured at maximum activation, which is not something that happens in vivo. Now, we could make a force length curve from a set of twitch responses or from a set of naturalistic patterns of activation. We would call that a submaximal force length curve. And it could actually have quite a different relationship than the classic ones you see in the textbooks. And so you already know something is not really being well captured just with a force length curve. when we talk about what's naturally happening in an animal, because I don't know about you, I'm not super strong, but still, even I don't typically have to activate my muscles to 100% in order to be able to walk around in the world, right? So rarely do we activate our muscles to maximum activation. Okay, so we might have a twitch response. We might have a force length curve. And then the last thing that we might do is we might have a force velocity curve. And so we might have the muscle shortening, and technically V here is going to be shortening velocity. I want to get the sign right, shortening velocity. And so here is like a static measurement with no shortening. And this curve will usually look something like this. And again, I'm not going to go into the shape of this curve too much. This would be a lengthening, or we sometimes call it in the muscle world an eccentric stretch. But again, the way that people usually measure this force velocity curve is they don't continuously let the velocity vary and measure the force. Instead, what you do is you hang a load of a certain amount of mass, and then you measure the maximum shortening that the muscle can do against that load. And so it's called an isotonic, or under a constant load. And actually, for those of you who are careful with your graphs, really these should be plotted the other way, because usually you put the independent variable on the x-axis and the dependent variable on the y-axis. And actually, technically, in these experiments, you're usually setting the force and measuring the velocity. But for these sakes, we usually plot them as a force velocity curve. But again, it's a static measurement. That it's not static like the muscle is actually changing because it's shortening, but it's a measurement made under a single condition, a single maximum shortening condition. And so it's again usually done under maximum activation. You could make a sub-maximal force velocity curve. But it's really important to understand that these classic ways that we describe muscle are under very special situations. That doesn't make them bad, but it makes them really important to think about. And they're really useful for examining certain hypotheses. In fact, the force length curve was originally developed to actually test the sliding filament theory, not to try and characterize the function physiologically of muscles. It's been used a lot to do that, and we can make interpretation of that. But we want to be really careful about how we interpret that muscle. From the force velocity curve, we could also take force times velocity, and we could get the power as a function of velocity, and this usually has some intermediate maximum. And I think that was covered in a couple of workshops before. But I'm not going to belabor these points too much, because this is sort of the classic way of characterizing muscle with what we would call quasi-steady measurements. What I want to talk about today is what do we want to do if we want to characterize the function of muscle under in vivo conditions. So in an in vivo setting, especially, I want to think specifically about a steady gait now, what's going to be happening is the muscle is going to be shortening and lengthening, and it's going to be producing force at various points in time in that cycle. And so for a sake of argument, I want you to think about, for the next sort of muscle, I want you to think about one of your glute muscles in your butt, right? And so if you think about this muscle at the beginning of when you put your foot down, so this is just my sketch diagram of your hip and your leg, right? When you first put your foot down, if you're walking or running, this muscle back here is going to be really long. And then at the end of that stance phase, it's going to be short. Okay, that's again my best capability of drawing that. All right, so what we can look at is we might have a plot of the length of the muscle versus time. And let's say, for the sake of argument, that this muscle is oscillating, it is cycling around its resting length L naught. It doesn't really matter for this. And so it's undergoing something where it starts out really long, and then it shortens and it lengthens, and it shortens and it lengthens, and it shortens and it lengthens, okay? And I've drawn this a lot like a sinusoid. It doesn't necessarily need to be a sinusoid. A lot of muscles are not sinusoidal in their deformation. It could look something like, it might look something like this, where it shortens really rapidly and then is fairly stationary and then extends really rapidly. But the key thing here is, even if it's not like a perfect sinusoid, it is periodic. Okay, that means it's repeating in a regular cycle in time. So let me now plot another, and during this cycle, the muscle will be producing some force, okay? So I'm going to pull out one cycle. And for the sake of this, I'm actually going to go from the start of swing to the start of the next swing period. So this would be the start of one swing cycle where you were bringing your leg forward. Then there'd be the start of stance through here, swing through here, and then you would start swing again at this point. Okay, so I'm going to pull out that one cycle and plot it very carefully here so we can look at some relationships. So we're going to now plot in orange. I'm going to plot time and length. Okay, and we're going to start off short. It's going to lengthen. Remember, it's not this muscle that's causing the muscle to lengthen, right? Muscles can't force themselves to lengthen unless they have a passive tension that's pulling them back out. It's the antagonistic muscles that are actually pulling on this muscle and lengthening it back out during swing. And then it produces force. Okay. And I'm going to draw now on top of that what the force of this muscle might be. Okay. So let's think about that for a moment. If it's my glute muscle, it's probably going to get and it's providing a lot of power during a stride. It might develop force right before the onset of stance, right? Right as I'm putting my foot down, it's going to start developing force and driving that leg through its stance phase. So I'm going to start the force at 0 here, right before the peak here. And here I'm going to try and be very careful with my drawing. Let's say it goes, so it's going to start here, it'll start to develop force, and it's probably going to peak its force like halfway through stance. And then that's going to drop off, but it won't be fully done by the end of stance. It's going to come in like this. Okay, so now I have my force and my length as a function of time. And I might also say that probably the activation of this muscle occurred somewhere right along in here. It probably got some EMG activation as it was developing force, and maybe that EMG activation continued for a little bit through here. I'm just drawing where like the stimulation would be as sort of idealized spikes. Okay. What we do in a work loop is I'm going to jump to how we plot it, and then I'm going to interpret it for you. What we do in a work loop is instead of plotting force and length as a function of time, we plot them as a function of each other. So now I'm going to plot the force on the y-axis and the length on the x-axis. All right. So let's do that, and let's decompose this into each of its stages. I'm going to call this point in time point 1, this point in time point 2, this one 3, this one halfway through 4, and then I should really extend this axis just a little bit. And then this will be 0.5, but I want you to note that because it's the same, this is also 0.1 right here, right? It's the same, it's gone back to the same condition. It's periodic, okay? Everybody see that? So now I want to plot this on a work loop. Well, I've started off where the length is the shortest here at 0.1. So I'm going, but the force is not 0. So I'm going to make a 0 mark here, and I'm going to say, okay, and here's like the L min, and here's the L max, and here's my rough middle point. Well, not, since we did it around the center point. It would be like here. And so the force is starting off at some significant value at L min right here, right? The force is dropping as the muscle lengthens. And so 0.2 is here. Then the muscle continues to lengthen and the force is starting to develop because we've started to activate it. That's 0.3. And then the force goes up quite high, and that's 0.4. And then it comes back around. So now I've plotted force as a function of length, and I've made a loop. Because the system is periodic, it's always going to come back to the same conditions again and again. So if I go through another steady stride that's exactly the same, this muscle is just going to go through that same loop. Okay. And notice that the loop is going in this direction. That's going to become important. So that's what we call the work loop. But what do we mean by work? All right. We'll talk about mathematically what work is in a minute, but I just want to go over what work is conceptually first and why the heck we would want to measure it. I'll talk to you about how work is related to that plot in a minute, but if we step back to what work is actually in the system, the mechanical work that is done on a system is equal to the change in the energy of the system. That's called the work energy principle in physics. And there's two kinds of energy that we can talk about changing in the system. We can have a change in the kinetic energy, which is related to the velocity of the system. And we can have a change in the potential energy, which is usually denoted U. And potential energy is the energy that can be stored against a conservative force, something that's like an elastic element or gravity. And in fact, those are usually the two that we talk about, is a change in elastic energy and a change in gravitational energy. So if the muscle pulls a mass up higher, then it changes the gravitational potential energy. If it stores energy against a spring, it changes the spring potential energy in the system. And if it accelerates the system, changing its kinetic energy, then it's changed its kinetic energy. So work has different ways that it can change the energy in the system, but work represents the total change in energy of the system. So it's a really useful value to measure because it has the units of energy. The units are joules, just like energy, and it tells you how the system's energy is changing. And here the system is the muscle or the body that encompasses it, depending on exactly how you're tweaking it. Okay? So what is work now? How do we calculate it from those values? Now, you might have heard that work is equal to force times distance, or in our case, maybe force times length, right? Some people have heard this before. Maybe a few hands. Okay, good. A few nods, right? So this is no, that's not what work is. You might more technically, work is force times the change in length of a system, but that's also not right. Don't write that. I really want to emphasize, I'm going to be very pedantic here for a moment. What work actually is force dotted with the change in position of the system. And the reason why I write it like this is that we have to remember that force and positional changes are vectors. They have direction, and work is not. It's a scalar, it's an energy. And so you can't just multiply two vectors together in a generic sense. You have to do a particular kind of vector multiplication. And there's different kinds. There's cross products. In this case, we do a dot product. And what that dot product represents, and this is actually, I'm not just doing this because I'm an annoying physicist, promise. I am that, but I was a biologist first. This is actually useful, is what a dot product actually tells you is if these two vectors are not aligned with one another, let's say that this is force, but the change in position is along here, like that would be the direction of the velocity of the system, right? The only work that's done is the part of the length change and the force that are parallel to each other. If the system is being pulled in a non-parallel direction, that does not contribute to the work, okay? So actually what you're looking at here is the only part of delta x that contributes to F, that contributes to the work with F, is the part that lies along this axis here. And if we look at it mathematically, then what work is going to be equal to, if we keep that dot product there, the change in X and F, going to be equal to the magnitude of the force times the magnitude of the change in X times the cosine of the angle between them. And most of the time, these things are going to be parallel with each other. So most of the time, theta is going to be equal to 0, and then cosine of 0 is 1. And so this is going to equal the magnitude of F times the magnitude of X, and that's where you get FD, force times the displacement, okay? Or actually the distance in the magnitude. But that's not always the case. If we don't measure length and force in exactly the same axis with the same experimental tool, you have to remember that the work done is actually the projection of the two. And this becomes really important for muscles that are at angles, or if you're measuring force and length change at different points or with different tools, like if I have a sonomicrometry crystal and I have a force measurement in a different axis, I have to take that dot product in order to actually calculate the work that's being done. It's also really important if you're trying to measure the work on a joint or something like that. So I'm being a little formal here because that formality reminds us that there are some important considerations when calculating work. But for the rest of this, let's say we've done that appropriately, and we're going to measure force and delta X in the same direction. We're still not quite done. And the reason why is that if you ever do a work loop experiment, you are going to pull your hair out, you have hair, because you will always get really frustrated with the sign convention. And I guarantee this will happen to you. So I'm going to try and make it a little easier because I've spent way too many hours of my life thinking about signs in MATLAB as trying to analyze this. If I have this muscle here that I've plotted out, I plotted length here, right? And I said we usually measure force in this direction, F, because we usually have a convention in muscle physiology that force in the shortening direction is positive. But we want the muscle to be doing positive work if it's shortening with a load. That means that delta X has to be positive in the shortening direction too. And that's why I called it delta X and not delta L, is delta X actually has to be in this direction as a positive in order to get the right sign on your work. Okay, so this becomes a real pain in the rear, not just because I'm talking about butt muscles, but because I'm actually talking about work loops and their sign conventions. And so really actually delta L has to be minus delta X with the typical convention that we use. If we're talking about L as being the actual length and going positive in the lengthening direction, then we actually have to set positive delta X in the shortening direction, or we won't get the right sign on our work. A lot of times people take care of this just by saying, oh, well, the muscle must be doing positive work when I go in this direction, so I'll set my sign convention to be doing it correctly. Trust me, do it formally because it will make it a lot. It'll make sure that you don't make mistakes. And with complicated work loops, it can be really hard to figure out which way it's supposed to look. Okay. So then what we have is we have our nice work loop here where we have, I'm almost done, 1, 2, 3, 4. And during the swing phase, the length is increasing of the muscle. And so during the swing phase, force is still positive throughout all of that. Length delta X, though, is negative because the length is increasing. That means delta X from our sign convention has to be decreasing. And that means that the net work is during swing is negative. And that's right? Any force that the muscle is producing is actually resisting the lengthening of that muscle. And so it is doing negative work on the system. It is reducing the energy in the system, not contributing to the energy in the system. The delta E system is negative. So that's actually the integral under the force length curve here, where W net now is the integral of F dx. So that's the net work, not the instantaneous work that we're doing. Okay. Now we can do it during, so that was during swing. Now we can do it during stance. During stance, the force is still positive. Now delta X is positive and the work net is positive. And that's going to be the integral under this curve. And when we do this integral under this curve, we still have to integrate all the way down to 0. And so you can see that the area that's encompassed here inside the loop is the network during stance minus the network plus actually the network during swing, but the network during swing is negative. And so it's going to be overall less, and that's going to give you the total work. And because we're going around in a loop, this, I should have drawn that in blue, this kind of description gives us the network that the muscle does during a cycle. Okay. Almost done. I just want to show you that there can be other kinds. What happens if I have a muscle that is doing the opposite of what I just showed you? What if I have a muscle that is resisting movement? Okay, so when it is shortening, going from, so now it's going to start at its long point. Here's like an F of 0. Let's say during shortening, it doesn't actually produce very much force. All right. So this would be like 1, 2, 3. But then it produces a lot of force when it's being actively lengthened by the interaction with the environment or by other muscles. This is like what your quad does when you're going downhill to some degree. It doesn't look quite like this. I have Monica listening, so I have to be a little careful, but an idealized one, okay? The pure braking quad. And I know there's more muscles than just the quad, but I'm an invertebrate guy. So I'm trying to be relating these things. What's happening here is notice that the loop is going in the other direction. Now, now during swing, there's a lot of work being done. And during stance, there's only a little bit of work being done. And so now the network is going to be negative. And this muscle is acting like a brake. It's dissipating energy from the system. So when we say we have a brake-like muscle, that's what we mean. It has a network loop that's negative. You can have other kinds of work loops. You can have like a force length curve that might look like this. Well, in this case, there's almost no area inside the curve. The amount of work done during shortening and lengthening is almost exactly equal to each other. So the net work here is about 0. But this muscle is actually acting a lot like a spring. If you notice, the force is approximately equal to a constant times the change in length, and that's going to be equal to minus k delta x, and that's Hooke's law. That's the law for a linear spring. So you can have a spring-like muscle that does 0 net work. But you can have other kinds of network 0 muscles. You could have a muscle that produces a lot of force but doesn't change length, and then changes length without producing a lot of force. So this one, again, work net is 0. But this muscle isn't acting like a spring. It's acting like what we call a strut. It's transmitting force, and then it's shortening with no force. And finally, you could have a work loop that looks like this, right? Here, this part of the work loop is going counterclockwise, and this part of the work loop is going clockwise. And so if we go back, remember that when we're going clockwise, we're getting negative work. And so here we're getting a region of negative work and we're getting a region of positive work. And so this muscle might have net work equal to 0, but that doesn't really capture its function. What it's really doing is in one part of its cycle, it's producing significant positive work. And in another part of its cycle, it's producing equal amounts of negative work. So it's resisting motion and dissipating energy for part of its cycle, and it's doing net positive work for part of its cycle. So just reporting the fundamental base value of here is the net work still doesn't fully tell you the function. And one of the things that you learned a couple of lectures ago is that a lot of what we're doing now in sort of modern work loop experiments is interpreting not just the total network across the full cycle, but the work over different regions of that cycle, because that tells us how energy is flowing through the system during those times. The last thing that...
Really quick with a question.
Yep.
All right, so I think this is wonderful. I'm really happy to see this. In the figure at the top, when you said this is behaving like a strut, can you maybe elaborate on that and sort of relate that to the mechanical analog of a physical strut?
Yeah, so a physical strut is something that doesn't change length, is very rigid, and transmits force from one end to the other, right? Well, that's what this muscle is doing. During the point where the muscle is developing significant amounts of force, it's not changing length. Right? It's all at a constant length. And then maybe for another part of the cycle, it changes length while it's not resisting or contributing to that length change at all. It has another, it's just totally relaxed, right? Another strut could, not have this region to it. It might just go like this. It might just not change length much at all, right? And you could have a mixture of these things, right? You could have a work loop that looks like this, that's a springy work loop. It's something that looks like a spring, but it does still have significant negative work to it, or maybe it has significant positive work, or maybe it has significant negative work if it's going the other direction, but it still is sort of tilted, so it's still spring-like. So there's a lot of ways that you can look at these work loops and interpret the different parts to it. Thanks for that clarification. That was really helpful. The last thing that I want to say is that there is one other term that you really need to know if you're going to read the literature about this stuff, which is that sometimes instead of plotting force versus length, we'll plot stress, which is usually denoted sigma, versus strain, which is denoted epsilon. And we'll do a stress strain curve. You might say, why the heck are we doing that instead of force length and force length? Well, I want you to remember stress in the muscle literature is usually force divided by cross-sectional area, right? And strain, people don't define strain very well. Strain is actually the change in length over the resting length usually, or the operational length, depending on the work. So we'll denote it as delta X over L naught. And so I want you to notice that this has actually very similar units to force. Let's take stress times strain, like if we integrated it. And what we're going to get is we're going to get force over area times delta X over L naught. What we're going to get then is that top part is that net work, right? And the bottom part is an area times the length is a volume. And if we assume the muscle has a density of water, the standard assumption that we make about lots of things, that's not always good, but then that's approximately equal to the net work over the mass, right? And if the scale, and so if you do a stress strain curve, what you get is you get mass specific work as opposed to work. Okay, so if you do a force length curve, you get work. If you do a stress strain curve, you get mass specific work. And the last thing that we have to do is we just have to say mechanical power is equal to the net work divided by the period of time that it takes to do that. Since we're talking about steady cycles right now, we can remember that the period of one cycle is equal to 1 over the frequency. And so the power, the mechanical power that the muscle is producing is the net work is the net work times the frequency. And if we do a stress strain curve, then we'll have, and when we're dealing with stress and strain, then we'll end up with the power over mass. We'll end up with the mass specific power. Okay. So power and mass specific power. Mass specific just means normalized to the mass. We actually sometimes we'll normalize to the muscle mass. Sometimes you have to watch the literature to normalize the body mass. It isn't always very good because the muscle mass won't necessarily scale with body mass. So you should be very careful what you're scaling to, especially when you're reporting the values and trying to calculate that, because really you should be normalizing, because based off of the equations of what stress and strain are, if you're reporting those, you should be scaling to muscle mass, the cross-sectional area times the length. And you should use operating length for that measurement. All right. I think I'm done here. I want to get over to the demo because it's actually literally live. So, but Catherine, I can take a question now and we'll have some time for questions afterwards too.
Sorry, I did not mean to click that. That was an accident.
Oh, okay. Any other questions that I can clarify on this before we go over and see the rig?
Any questions here? I think we're good.
Okay, I hope that was clear. Oh, there's a couple of things in the chat. DOT, that was a dot. Yes, thank you, Christian, for clarifying for everyone. That little dot that I was making, we sometimes think that dot is a multiplication, but when you have vectors, it's a formal vector. It's called the scalar product. It's a product of two vectors in that way. Okay, now I'm just going to give you the orientation slides for Ethan's thing here. So what Ethan is going to show you next is we're going to actually show you the work loop from a moth. We're going to use a moth, and specifically we're going to use the power muscles that power the wing stroke. And it's actually very nice in a moth. Part of the reason why I like to look at it is that when insects are flapping their wings, there's no muscles in the wings. All the muscles are in the thorax, and it's an insect. It's got an exoskeleton. So the exoskeleton is on the outside. So the muscles attached to the exoskeleton. And the weird thing is that the muscle that produces the downstroke doesn't attach directly to the wing. Its origin is here and its insertion is up here. And if you watch this little area that I've circled here, it is contracting and it's actually deforming the exoskeleton like an elastic shell. And so the downstroke muscle is this DLM muscle. It goes from up here by the head to back here by the abdomen. And when it shortens, strain propagates across and causes the wing stroke to go down. And that is the main singular muscle that produces mechanical power to drive the downstroke of the wing. Okay. So it better produce net positive work. Otherwise, the moth isn't going to fly because there's no other muscle that can produce that positive work. If I just show you a cross-section of the musculature, these are some recent CT scans taken by Joanna Baker, who's one of the IMSI summer students here at Georgia Tech. She's reconstructing all the musculature. The main big dark green muscle in here in the middle is the one that we're going to be looking at, and that's that dorsal longitudinal muscle. And these muscles basically act as a single motor unit. One of the nice things about working with invertebrates is that effectively there's only a single motor neuron going to that whole muscle. So the whole muscle is activated like a single motor unit. And that's true for most of the muscles during fast movement. So actually, if you like, what we can do is we have to know the natural pattern of activation, because what we're going to do is we're going to take the muscle out, we're going to drive it through its normal length change that it would experience, and we're going to stimulate it at the typical phase of activation where the animal would normally stimulate it. So we're going to prescribe length, we're going to prescribe stimulation, and we're going to measure force, and then we're going to plot force versus length. In order to do that, we have to know how the muscle is normally activated. So like many people, we take EMG measurements. We can do that by putting wires into the exoskeleton. Here, there's actually 21 wires implanted into this moth, done by Rachel and Joy in the lab. And as the animal flaps now on a tether, we can record the activation of all of these muscles. And so when we look at this, we have a bunch of different muscles and we can record the electrical activity. And this does not look like a vertebrate EMG because, again, each muscle is basically a single motor unit. And so we see all of the activation being in precise muscle action potentials, these discrete spikes of activity that you see. And these are the electrical signals that the animal's brain is sending to its nervous system is sending to its muscles to activate them. So we're going to go look at what Ethan is going to do is he's going to isolate the DLM, the downstroke muscle, the big red muscle now. We've recorded the level of the pattern of activation, and we're going to play back that pattern of activation at the right phase during the length change. And you can see this sort of nicely in this animation by Andrew Montcastle. Here inside the moth's thorax is going to be the muscle. It's going to be the dark red now that we're looking at. And as that muscle contracts, it actually just gets a single spike of activation during each contraction. So it's about the simplest work loop you could imagine. It's going to get basically a twitch of activation at a specific phase in the lengthening cycle. And we've mapped those out before. And so what we're going to do is we're going to play in the length trajectories, and then we're going to pop that muscle with a single spike of activation at the right phase, at the right timing relative to length. And we're going to measure the force it produces. When we go over there, what you're going to see is you're going to look at a setup like this. You're going to see an ergometer here. And that's a thing that both moves the length of the muscle and measures the force from the muscle. A very clever little motor setup. We also are going to have a saline drip above it. You're going to see this live in just a second. I'm just orienting to you on a slide. Then we're going to put the whole thorax in here. So we're going to mount the entire thorax of the moth in here. And we're going to do that so that we can set the operational length of the muscle to the right point. And then what Ethan's going to do is he's going to dissect out a ring of exoskeleton around the thorax to mechanically release the muscle from the exoskeleton. So we're going to have a patch of thorax on one side and a patch of thorax on the other side, a patch of exoskeleton on each side that the muscle is attached to. And then we're going to squish those two pieces of exoskeleton next to each other, mimicking the length change that the muscle produces under wing strokes. And then we're going to measure the force that muscle produces. And we can do that simultaneously with the ergometer. The ergometer is really nice because it forces the length and the force measurements to be in the same axis, which gives us the, lets us ignore that dot product or simplify that dot product. Okay, so here we have the patterns that we see. So the other things that are going to be here, the other things that we're going to see here in the rig, there's a peristaltic pump here that's going to be pumping saline through tubes that go into that saline drip. The saline drip has a little heater on it so that we can control the temperature of the muscle. These flight muscles actually go up to 35 degrees C during flight. They actually have to get hot enough to produce positive mechanical work. And then we've got a temperature controller to set that temperature. Then we have this coolant system to control the temperature controller, to allow the temperature controller to heat up and cool down. And then we have this stimulator here, and this is where we're going to apply this. We're going to use wires from the stimulator to pulse that muscle and stimulate it with those individual action potentials. You can grab onto a nerve and do it that way, but we're just going to directly stimulate the muscle. We found that that works really well for these invertebrate muscles. So we'll pop it with a little action potential. We'll induce a muscle action potential at the right phase, and we'll measure the force. And then here's the ergometer controller where we prescribe the length change, and we've previously imaged the contraction of the thorax from that video I showed you at the beginning, and we know the pattern of length change. And finally, in the background, you see Luke Marsh here. He's one of our he's a graduate student, he's a master's student from Clemson, who's working with us over the summer as one of the IMSI exchange students. All right, so that's what you're going to see when we walk over there. I'm going to bring us over on the iPad, and I will answer any questions as we go. I'm going to, but give me a moment to switch this as I go. It's always tricky to use multiple devices. I have to turn my audio off here. Okay, can everybody hear me on here?
Yes, we hear you.
Yes, okay. Give me just a second. I will not turn on the video until I get over there so you don't get motion sick. Actually, I will. Walking down Georgia Tech, we can switch the camera so you see we're walking down to my lab. There's the various posters. There's Varun, a graduate student in the lab. Kosh, a graduate student in Dan Golden's lab. Delaney's an undergrad working with us. Oh, and Ethan's not here. Let me find Ethan. Oh, there's Ethan. Here comes Ethan. So this is Ethan Wold. He's a graduate student in the lab. He's the IMSI summer students, and he's getting ready to mount a thorax onto the ergometer. So as he does that, we're going to point out the various devices that we've looked at here, right? So in here, oh, Ethan, you want to describe what you're doing?
We can't hear Ethan very well.
Hold on. Go ahead, Ethan. Can you start again? I had it on the wrong audio.
Oh, okay. Yeah. This is a thorax that I think Simon oriented you to, the anatomy. There's a big muscle that runs this way. And we're basically going to try and fix the ends of that muscle so that we can get its length along the line of action of the muscle. So I'm going to put this kind of custom mount on the posterior side. And I just have some glue on these prongs that's allowing me to do that. You can see it's still kind of going a little bit crazy right now. That's what happens in insect muscle.
So the ganglia, the nervous system and the central part of the insect is still inside that thorax. And with insects, the brain basically inhibits a lot of things rather than activates. So when you take the head off, it actually releases the central pattern generators in the thorax and causes contraction. This is really interesting for cockroaches. If you cut the head off of a cockroach and you feed the neck stump, you can actually keep it alive for a month and it will just run. That's all it will do. Right, so fun fact about cockroaches if you needed to know that.
I'm stopping that right now by snipping the ganglion.
So what he's doing, he's bringing his scissors in and he's cutting all the motor neurons to the muscle. And he sort of knows exactly where to cut those. We validated that with dissections before. And that prevents any natural stimulation of the muscle. So now the muscle is totally quiescent and passive until he puts the electrodes in and stimulates it.
So the other side, the anterior side, is going to be fixed with a custom 3D printed mount that will fit the contour. That will fit the contour of the moth. So we custom design a 3D printed mount. Sorry, it's hard for me to talk and do this at the same time. Okay.
So now he needs to rigidly attach this to the other side of the exoskeleton so that he has a rigid attachment against which to push. And so he's mounting that custom 3D printed piece against the exoskeleton on the anterior side of the muscle. And I'll give you a zoomed in view in just a second. I just don't want to interfere with his experiment. And bear with us, this takes a minute. You're actually seeing a live experiment. This is a viable prep, so we could actually get data from this prep. So we're going to try and do it real so that we don't waste animals.
So that is more or less set up.
What he did there was we fixed with the cyanoacrylic glue to the exoskeleton, and if you just sprinkle baking soda on, it automatically sets the cyanoacrylic. So that's what he was doing with the white powder. It was baking soda, baking powder. Trust us, white powder. Now he's started the peristaltic pump over here, so he's pumping saline through the heating device below it, and then that's coming up through the heater, which is the black tube that's mounted here. He just has to have the saline ready. Right now, the thorax is fully encased, so there's still the hemolymph, the insect conversion of sort of blood that is encasing the muscle and keeping it moist and alive. In a minute, once he cuts open the exoskeleton, that will leak out, and he'll have to drip saline on in order to keep the muscle viable.
Is that my latest prep of all time?
So you could prep the whole muscle separately. You could dissect the whole muscle out and then mount it on here. And people do that for various kinds of muscle preparations. The one thing that's a little bit difficult there is you have to set the operating length. And so if the muscle totally relaxes, you have to know what length to stretch it back out to. The other thing that can happen is if you do that, muscle, if you just allow it to sort of passively shorten to its maximum shortening gait, like if you release all tension on it, oftentimes it will hypercontract. And then when you pull it back out, there'll be a lot of micro damage that will make it hard for it to behave physiologically in the right regime. And so we like to keep the muscle under constant tension. So what we're basically doing is we're going to mount the two ends rigidly, set the tension so that those are then maintaining the tension, and then release the exoskeleton so that we're not measuring the work that the exoskeleton is doing. We're just measuring the work that the muscle is doing inside of the exoskeleton.
So at this point, if you wanted to do anything to make your life easier in the prep, now would be the time to do it. So what I mean by that is I've learned from doing a bunch of these that it helps put the electrodes in. If I pre-poke a couple of holes at this stage with an insect pin, so this is not probably how Simon would do it, but pre-poking 2 holes, that's not going to change the prep at all, but it's just going to make it much easier to insert my electrodes in just a moment. I'm just kind of still waiting for the glue to set.
And so what he's going to do is we've made these little tungsten rod electrodes. And because the exoskeleton is on the outside, we can make little pinpricks in the exoskeleton. It's very convenient having the exoskeleton on the outside. And then we can thread electrodes down through the exoskeleton so that they're touching the surface of the muscle, or that they're actually penetrating into the muscle in this case.
So Simon mentioned setting rest length, and practically speaking, what we do is there's been such a body of work on manduca sexta muscle in particular that we know the operating length is a fraction of the resting length. So I took can you define the difference? Yeah, so the resting length is a caliper measurement that I took before I put this moth on the prep. Is just like when you do the tick off the head and the abdomen, that's what the muscle length is. That's not necessarily what the muscle length is in vivo, because while the animal is flapping, doing its things, the exoskeleton might be putting tension on the muscle and changing its length subtly. And people have done this analysis and shown that the operating length is about 98% of the resting length. So what we do, practically speaking, is we have this thing set to its resting length. I will set it to its resting length in a moment, and then we'll just shorten it by an additional 2%. And that will get us to its putative operating length.
So when we set it to the resting length, what we're going to do is, since we now have it mounted on the ergometer, once all of the attachments are rigid, we can adjust the offset on the ergometer until the force that the muscle is pulling on the ergometer is 0. And that'll be the resting length. And then we'll go 2% offset from that to get the operating length. And then we'll oscillate the muscle around that and measure a workloop.
So I'm going to do that right now. So my glue is probably set most of the way. So we have a real-time force readout. And this is not something that you're never going to be able to get it exactly. And that's just because, the force kind of fluctuates quite a bit, but you kind of get it within a reasonable margin. So this is really close to being zeroed out. And in fact, the weight of the mount actually causes it to go slightly above 0. So this is totally fine. This would be acceptable for
And
zeroing
these,
out.
you notice the force out is in voltage. We have an internal calibration for what that is. About what's 1 volt on this?
It's a ×2 factor. So it's 500 millivolts 500 millinewtons per millivolt. Yeah. Okay. So at this point, I'm pretty confident that my glue is set. So what I will do is begin the dissection process.
For context, a moth muscle will produce anywhere between 700 to 2,000 millinewtons, so up to 2 newtons of force from that little muscle. They're very powerful. And so that error that we had on there was about 1 millinewton of force, so less than 1%. And this is hard to see. I'm going to walk around to the other side so that you can see it. What Ethan is doing is he's done this enough times he can do it without a microscope. He's going in and with a pair of very fine dissecting scissors, he's releasing the exoskeleton around the muscle. So he's taking the scissors and he knows where the muscle is, and he's just cutting along the sides of the exoskeleton away from where that muscle is, where he doesn't have to be very precise, and releasing all of the other material that would go between the 2 attachment points, such that the only thing that's going to be bridging the ergometer and the rigid red mount is the downstroke muscle. And he's trying to do this fairly quickly because as soon as he's cut in, of course, the muscle will start drying out, and we want to get it under a saline drip as quickly as possible.
So strictly speaking, at this point, it's probably all right, but generally we go a little bit farther just to give ourselves some confidence that we're not coupling the 2 sides of exoskeleton in really any way, because we want the only force that's being picked up on the ergometer to be the force being generated by the muscle of interest and not any other muscles that are around. Now, all the other muscles are small enough that, and we're not stimulating them, so it shouldn't be too much of an issue, but this is like one of those things where this is just how we do it.
And if we would do a few more verification and testing steps if we weren't sort of doing this under quick stuff where we would look at it carefully and check a few things, but we're just going to get it close enough because it doesn't really matter for this experiment if we have a few extra passive bits.
So time is money with this kind of prep. So the second you
walk around,
you're on a clock, and so you want to get to the point where you can supply the muscle with saline as quickly as possible. This is something of a specific thing for insect muscle in this particular prep. So if you're working with vertebrate muscle, or you're working with mouse muscle, or even if you're working with single fibers of insect muscle or whatever, you're probably doing this whole prep in a saline dish. So in those cases, time is not as critical. You can kind of take your time with the dissection. But the way that we do this, we supply the saline with a drip. So we got to get that going pretty quickly. And the saline is cold right now, which helps maintain the life of the muscle. We only heat it up right when we're about to do the experiment.
And because the muscle is pretty small, we can heat it up very quickly.
So the next step is going to be to put the electrodes in. And if you don't pre-poke holes, then this tends to be a very annoying process. So that's why I did that earlier.
And you show the tip of one of those electrodes before
I'm just untangling them. These are the electrodes. So this is a tungsten tipped silver wire. Can you see that on the camera at all? Can't really pull it.
It's very thin.
Right. So we have 2 sets of electrodes. So 2, hot wires and 2 kind of grounds, or, 2 positives, 2 negatives, but it's a differential stimulus basically that we're putting in. And I'm just going to essentially poke 1 set of electrodes into each muscle, and they run parallel to one another. And again, I kind of know where these muscles are, so I'm doing it very quickly and without worrying too much about exactly where they're going. It's because I know where I'm putting those electrodes.
Closer in view in just a second. We need to position these electrodes such that we stimulate the whole muscle and we make sure we get all of the fibers activated. Or otherwise we'll only be getting the work from a part of the muscle.
Okay, there. So that was pretty good. It only took me a few seconds If I didn't pre-poke the holes, then that would have taken way longer. Okay, so now we can see if we're gonna get a viable prep by just doing a couple test stimulations. So our stimulator has a trigger, and I have a scope set up over here. So this is where you kind of see the output. So you can also show them the muscle twitching on the rig.
What we're going to do, yeah, so maybe I'll show the muscle first. So what we're going to try and do is we're going to try and activate the muscle, and you should see the electrodes move slightly, even though it's held at a specific length. Okay. Can everybody see that online, the little twitch? Okay, good. Good thumbs up from Monica. She's used to looking at twitches this. So. All right. So that means that we've got a viable prep that's working there. So now we can measure the forces that it's producing, and we're going to go a little fast, Ethan, because we're running out of time. We're going to skip how we sort of calibrate the stimulation. Basically, we find a threshold at which the stimulus is producing a decent amount of force, and then we can fairly reliably generate that. Is that the stim that we're looking at, or is that the force?
That's force.
That's force.
Yeah.
Okay. Yeah. So you can see the force twitches that we're getting out of the muscle as we getting a little bit of downward ring. Okay.
Okay. So at this point, I would basically just turn on the temperature control. And then in about, 60 seconds, the muscle will be brought up to temperature. This is what's heating up the saline, and the saline is dripping on the muscle that's heating up the muscle. And I'm not doing the verification where I put a thermocouple in there. We've done that a bunch, and this system works very well. But in general, you would want to be monitoring the temperature of your muscle while you're doing the
One of the questions we get as we are waiting for those 45 seconds for it to heat up is, why the heck are we doing it on this kind of rig rather than like in a dish or in a larger rig? You'll notice that the profile of this rig is extremely narrow, right? That's because we'll take this entire rig up to Argonne National Lab, and you'll slide the whole rig into the X-ray beam such that you have the synchrotron shooting right through the muscle in this axis. And we'll be able to, while we're doing work loops, measure, image the molecular activity of and spacing of the myofilaments inside the muscle using the X-ray beam. And so we've had to design this whole rig so that it's very narrow in one direction so that we can slide it in and out of the X-ray beam.
Okay, so this is basically up to temperature. 34 degrees C is roughly what we keep it at, which is actually slightly less than the actual temperature that the muscle experiences in vivo. These muscles get very, very warm. And then at this point, I would just start my work loop script, and I think we should probably just move.
So we'll try and have them watch one work loop. So the wing beat frequency of this moth is 25 hertz. So we're going to do 10 oscillations of this muscle, but that's only going to be a fraction of a second because this muscle oscillates so quickly in the actual organism.
So you'll see it a few times. So,
and one of the things that we can do is, okay, you'll see it, watch it a couple of times and you'll see it. Oop, that was 10 wing strokes right there.
Yes.
And so that gives us 10 work loops from that. It's an extremely fast muscle. This is actually a relatively slow insect. For reference, like a mosquito would be contracting its muscle 1,000 times a second, which is pretty crazy to think about. And so this will give us we're prescribing the length change, we're stimulating the muscle, and we're recording force. So we now have everything that we need from the introduction that I gave to plot the work loops for this. And the data that we've shared on the IMSI drive is actual recordings from a moth work loop here. But what we've done is if we stimulate this muscle at the natural timing of activation, it produces force during shortening and does positive net work. If we change the phase of activation, we can make this muscle operate like a brake, even though that's not what it would do in vivo. And so we've done some phase sweeps where we activate the muscle with that single pulse of electrical activity at different times in the shortening, lengthening cycle that it's going through. And we measure the differences in force. And this is one of the ways that we characterize the power curve of this muscle in vivo. So, or equivalent to in vivo. All right, so it's all done now. That was an experiment. We actually got the data. We did actually record all of that data. So now what we're going to do is we have about, thanks. We have about 15 minutes left, which is just a little bit of time. So we posted 3 files that are in CSV format. And if you can pull those files down, each one of them is very simple. It has 3 vectors in it. Are they vectors separated out and labeled as force, length, and stem?
The 3 columns, I put
Three
in the
columns.
README what they are. The first column is length, the second column is force, the third column is stem.
So what you can do is find the length, the force, and the stimulus. And what you probably want to do first is just plot all 3 of those columns versus time so that you can see their pattern.
Yeah, I didn't give them time vector, but I told them the sample rate, but they can just plot them.
Yeah, you just plot them as points. There's no explicit time that we have it sampled, so you can just plot it as samples. It won't matter when we plot force versus length. Thanks, Miles. Yeah, Miles just posted the link in the chat so that everybody has it. I appreciate that. We didn't.
I'm gonna go on my computers.
Ethan's going to walk over to his computer so that he can help us. I'm going to bring this over so that he can talk us through that data if he needs to. So your challenge here is we've given you 3 files. The README has the vectors in them, the columns labeled again. Again, it's length, force, and stem. And what you want to do is you want to plant, instead of plotting them against time, you want to plot the force versus the length for each of these 3. And then you want to, and then our challenge for you is in the last 15 minutes here, figure out which of those files is a positive work loop, which one's a negative work loop, and which one is doing about 0 work. Ethan, you're on your computer, so you can talk through your computer.
Yeah.
And Ethan and I are here. I'm going to go back to my office and turn off the video on here so you don't get motion sick again. If you have, we'll chime in a little bit as we go, and Ethan will plot the data and share his screen at the end too.
Thank you. We're working on it over here.
Yeah, please let me know if there are issues with it. I tested the CSVs in MATLAB, but if you're plotting it in Python or something, hopefully you're able to load everything.
Okay, well,
Yeah, I'm sure.
I think we have, is everybody using MATLAB? Are you using other things? Here. I think
I'm
Alyssa used-
MATLAB it over here.
Yeah.
Okay, so Ethan and I are, sorry. Ethan and I are back at our computers now, and we can help out. But you basically just want to do a quick time series and plots, and then you want to plot the force versus the length if you haven't already done that. Make sure you get the order right so that it's force versus length rather than length versus force. And the trick will be figuring out which direction those plots are going. And if anyone has any questions, we can also answer questions now as you're going along.
Do we buzz in or do we send you the answer when we got it? Like Jeopardy?
Let's if you've got the answer, just hold on to it for a few minutes and let's let everybody get a shot, and then Ethan will go through the answers at the end.
Buzz in.
Though I appreciate the eagerness, Christian.
Always, Simon, always.
And as you may be realizing, we've given you real data, which means it's messy. It's not perfect, exactly overlapping loops. And that's because that's what you would normally experience if you were recording Workloop data.
We have graphs over here, so we're working on interpreting.
We do. Don't forget to label them. I did not with mine.
Does anyone need help generating their plots?
I think we're good over here. It's just taking a little time.
Yep. The interpretation is tricky. We'll give another 5 minutes or so, and we just want the last few minutes to go through the answers and the last couple of notes about what's happening.
Simon, this is Jill. I have a question just while we're plotting. Can you hear me?
Yep, shoot.
Okay, yeah, so I'm curious about, I understand in this particular purpose, you're removing the exoskeleton, but what have you learned by keeping the exoskeleton on? And I imagine you've explored that a bit, so I'm just curious what you learned from that.
Yeah, if you keep the exoskeleton on, the problem is the exoskeleton is a spring, and springs do work too. So you can measure the whole work of the combined complex by doing that.
Yep.
But you wouldn't know what portion is due to the spring and which portion is due to the muscle. And so we've actually done both separately and looked at and characterized the spring-like properties of the exoskeleton in that particular shape and the work-like properties of the muscle.
And I'm curious then, like with different organisms, right? So it'd be nice, you test it with an intact and then you remove the exoskeleton and then a test. Do you know the relative contributions of muscle? I guess an exoskeleton is a spring. Do you end up with variation in your between participants and the exoskeleton properties? Or the relative contributions, you know what I mean? I'm thinking about adaptations here and how it might vary.
Ethan, do you want to answer that? You've done a lot more of those measurements.
Sorry, I'm making sure my plots are.
Oh yeah, I'll let Ethan
Sorry.
answer. No. Yeah, I'll let Ethan do the plots. I'll answer. In general, like there's large changes with body size, but proportionally with that, once you sort of factor that out, it's not so we don't see a lot of particular tuning there. But we haven't done paired individuals where we would be able to look at that exactly. We haven't sort of. There's not a lot of variation in the exoskeletal properties. So the actual effective like modulus of the exoskeleton is very, very similar across individuals. The actual amount of energy that absorbs then changes a bit with the size, but so the springiness of it changes, but that tends to scale with size. But one of the biggest, we have a more fundamental problem, which is there's a dirty secret underneath all of this, which is that if you actually do work loops and you look at all the work loop data on manduca, or in insects actually in general, and you look at the raw amount of mechanical power that these guys can put out, that their muscles could produce, and then you do a simple back of the envelope calculation of how much power you would need in order to fly. Just like how much energy do I need to dump into the air to support the body mass? And that energy can't easily be recovered, right? Once it goes into the air, you might be able to recover it by moving your wing back through the wake. But assuming there's no sort of energy recovery from the air, you can't do anything with springs. You can store internal energy and exchange it, but to keep your body aloft, you have to push against the air. And if you do that calculation, we're off by like a factor of 4, maybe 8, meaning like the muscles are too weak to be supporting the moth.
Interesting.
And
Yeah,
we just don't know where that power is. We have some ideas, but it's sort of one of the annoying things in this, actually really interesting things in this literature.
Just as I won't spoil at least my answers, which maybe we hideously wrong anyway. Yeah, I'm looking at the number of the joules here. If I did my dimensional analysis right, doesn't seem like a lot of joules, but maybe it doesn't need that many joules. Anyway,
it doesn't need that many joules because it's only a couple of grams, but it does need more than that. And especially, and this wasn't a perfect work loop. We were probably, I don't know what force we got out of this, but it wasn't, we didn't quite tune it and do all the checks that we normally would do. So, but it's actually very hard to get these muscles to produce the amount of power that they basically have to be producing in vivo, because they're clearly keeping them off the ground.
Or you have to be careful because you're going to be one of those memes that says scientists say that they can't fly. It's be one of those memes like all over again, right?
Currently, Kirsten's referring to these old things that, like, according to classic aerodynamic theory, bumblebees shouldn't be able to fly, which is true if you make all the assumptions of classic aerodynamic theory, which definitely do not apply to insect wings. But according to classic muscle physiology work loops, insects should not be able to fly given the amount of mechanical power. So we're missing something. And we've been very curious about that. That's actually how I lured Ethan to the lab originally, I think, is by telling him the missing power problem. Of course, he worked on other stuff and still haven't solved it. You're not allowed to actually leave, Ethan, until you solve that problem, by the way. I haven't told you that yet, but that's not true.
Okay, so I'm now realizing that I think I gave everybody the wrong sample rate, which is probably not relevant for the exercise, but this was sampled at 50 kilohertz, which is absurd. So don't do that if you're doing your own.
Christian is very quickly recalculating his power.
Yeah, I
estimates.
Did. As you can tell, I'm sorry.
I heard the click on the keyboard.
Yeah, it should be closer to 10 kilohertz is more than sufficient. 50 kilohertz just makes all your vectors longer than necessary.
Can you share your plots and go through the answers now, Ethan?
Are we ready for that? Yeah, I guess we only have a couple minutes. Share desktop 2. Okay, so I forget which one I labeled 1, 2, and 3. I'm just going to go through 1, 2, and 3 first. So this is workloop 1, workloop data 1 should be. So you can see that there's kind of like a figure 8 vibe happening here. That's kind of getting larger in force amplitude as the stimulation kind of ramps up. that's like a pretty common feature of work loops, and it's why we do 10 oscillations, is because you tend to only get the sort of the best behavior towards the end after you've done a few oscillations. So yeah, this
So
one,
actually in work loop data, usually if you look at figures of work loops in papers, if you look carefully at the methods, people like us will say we tossed out the first X number of cycles because we're only trying to describe the steady state work loop. But now if you think about any actual animal moving, they're probably not at steady state for more than a few strides. So those transients are probably really important, and most everyone ignores them.
yeah. So I didn't compute the actual network here, but it would be pretty close to 0 because you're getting a figure 8 here. So the two lobes will kind of cancel each other out almost. I tried to find one that was like that. Okay. So the next one, this is work loop data 2. What do people think this one was?
Positive.
Everybody else positive? People get positive, negative? This one is a positive, is a negative. Sorry, this is net negative work. So
Lies.
this would be a clockwise dissipating. This would be a dissipating system here. Should be anyway.
And the reason why you probably got positive instead of negative may have been that sign flip that I talked about. If you didn't multiply the delta L by a negative sign, you got the sign of the work wrong. Thank you, Christian. I really appreciate it. He's never going to talk to me again.
Yeah, but this, I mean, it looks like if you don't, yeah, think about the sign correctly, you just look at it like there's not really a way to tell unless you look at it in both time and kind of work loop domain. Okay, and then I guess that leaves the last one. This one is the positive work production. So it's doing this counterclockwise loop. There's a little bit of a second lobe here, but this lobe definitely counteracts that. So the network production is going to be very positive. And if you zoom in, you can see that the force peaks after the length. So that is generally a giveaway that you're going to be producing positive work if things are close to sinusoidal, which they are close enough in this case.
And I'm only allowed to tease Christian there because I literally made that same mistake for like repeatedly for 10 years of like doing these kinds of experiments. And every time we do this experiment again, there is some time when we analyze the data and we put it up, and then we're looking at it at the end. We're like, wait a minute, all of our sign conventions are wrong. We've got to go back and reanalyze everything. Half the time we're right and half the time we're wrong, and it's a real pain. So make sure you watch your sign conventions when you're doing this stuff. It's a real hassle with the experiments.
Don't be like me, is what we're saying here. Okay, don't
me.
Be like me. Cautionary tale.
All right, we'll be on for a few more minutes. We're at 1:30, so we should finish up for everybody. But if anybody has further questions, Ethan and I can stick around and answer a couple of questions. Thanks for doing that plotting. I hope it was actually, I appreciate you all trying to actually engage with the data a little bit. It's good to actually try and do stuff. So.
Thanks for the live demo and for the example data. It's really good to have examples to play around with.
Thank you, Ethan, especially for doing the experiment on the fly on the moth.
Simon, I have a question for you. So I'm going to revisit a question I had, I think, in our first workshop about analyzing sort of portions of work loops. And now that this is super helpful, now that I can actually deal with some data. So now I'm imagining you take, your time series data, so you know where you are in different phases of a behavior around your work loop. And then, we're often interested in sort of how aspects of behavior change in different phases of a gait cycle. And so now I can kind of see how you might isolate a portion of the work loop that's, let's say, in the stance phase of gait, and then through this analysis, look at how the function of a muscle might change during that portion of the behavior. And is that something that you all sort of consider at all in your work?
Yeah, that's a really great question, James. Thanks for saying that. Not only is it something that we consider, but I think we all really need to be very careful with this, because we gave you a flight example, and flight is nice. There's a reason I went to flight for some of my research. Flight, the muscle is always acting against a wing that's always acting against an aerodynamic load. During terrestrial locomotion, a work loop is very misleading, because what is the work acting on is a question you should always ask yourself.
Yeah.
And when the limb is in the air, if you have a muscle that is producing negative work during like that swing phase, it's dissipating energy from the system the muscle is in. Well, that's the moving limb. When the muscle is in stance, it's producing a ground reaction force. It's pushing against a much higher inertial load, the ground. And the work that's being done is effectively being done on the center of mass of the body. And so the work being done during stance and the work being done during swing are in effect being done on different things. And so for terrestrial locomotion, it's actually always really bothered me to describe the muscle's power output or work output as just a single net value of the whole cycle. And for some of the cockroach stuff that we did before, it was really interesting to dive into these differences, because what you actually found is like during transient perturbations and such, what would happen is like a muscle would get recruited as from a brake and it would become a motor under a different pattern of activation. And the way that it did that is it actually produced a ton of force during, it was an extensor muscle, it produced a ton of force during swing. And that actually resisted the motion of the swing. It dissipated a bunch of energy and it forced the limb back on the ground really quickly and caused the animal to take a little sort of small step. And it got the limb back into the position where that muscle was shortening. And then it did a bunch of positive work. So it did a bunch of positive work by doing a bunch of negative work during swing to let it do a bunch of positive work during stance. And I think Monica's thought about this, Greg's thought about this with some of his perturbed work loop stuff. I think it's really important, especially in terrestrial locomotion, to think about where in the cycle the work is being done and do that a little bit more nuanced. So that was a long answer to yours, but yeah, I think is a really important point that we're going to in the whole IMSI group is it's not just network. We can call that one number, but please don't just report that number and think that you're done, because especially if it's like zero network, you've told me very little about the function of that muscle. It'd be a spring, a brake, a spring, a strut, or non-functional or bifunctional. Any other questions?
Yeah. Any questions here?
Wanted to show, I'll end with one picture. If folks, Greg Sawicki and I wrote this review on perturbed muscle work loops that I think he talked about a little last week. And I just wanted to, this is a paper that came out in JEB last year. And I just want to highlight this, that like I've done here, there's a sketch very similar to the one that I just made where like, if there's a steady muscle force versus muscle length curve in dark black here, you get this nice loop on the right. But then if you perturb the muscle, you get this like double force peak here. And if you plot that out, you get a really weird work loop that goes like here in black, and then it goes down like this, and then it curves back up in blue and down like this. And that's an example, I think, James, of like where we would analyze each of those phases during the perturbation and during the smooth transient part, and we would see a very different behavior of the muscle. So we could report the network, and the network will be different between the sort of perturbed curve and the solid curve. But that's a very sort of it's a very simplified approximation of sort of what the function of that muscle during that perturbation is. The muscle dissipates some energy, produces some net positive work, and it does it at different time there. So I think this is the kind of, we were advocating for in this paper is these kinds of, the work loop framework doesn't actually have to even be a loop. It could just be a force plotted against length, and you can interpret those things by integrating to get work, but be very careful by getting your sign conventions right and getting your target of that work right.
And I just wanted to add, maybe highlight that it's always important to go back and forth between the time series data and the work loops, because the work loop takes away that time element in the presentation. Yep. And so you cannot fully interpret the work loop without the time series data as well.
And be careful calculating net power too, because now you have to calculate the work over the region, over the time frame when that power is produced, when that work is produced, if you want to get actual power out, which is an extension of what Monica said. And I should say all these really awesome figures that you saw here and here in this paper and that Greg talked about were generated by Emily Abbott, who's on this paper with us. And she's done a really nice job of visualizing a lot of this muscle stuff. So thanks to her for that.
That's a very useful background paper for IMSI. So people should definitely go and read it if you haven't yet.
Question, that might take us into the weeds, but I do cyclic loading on tendons and I try to get those work loops and calculate the hysteresis. And there's like a handful of trials where for whatever reason, my loading curves, they should be higher than the recoil curves. So you should be applying more force, you know, rather than when you're letting it relax. And for some reasons they're switched. So I was just wondering if you guys had ever faced that problem and if there's like certain things that you look for, because I would think that if my force and length are both increasing at the same time, then those are good signs. If it was out of phase, then that might be a sign that there's something wrong with my time data. But yeah, if there's anything that comes to mind right now, or if maybe I can talk to you on the side and show you some data for some help, anything would be great.
Miles, could it have something to do with this vector problem that if the alignment of the force and displacement are changing between the loading and unloading curves? And so you're assuming that if you're making an assumption that the alignment is constant, then that could cause some weirdness
Right.
between loading and unloading.
That's actually, yeah, I was thinking, I have not done any of the vector stuff in my current calculations, so that could definitely be a problem.
It depends. How to do that is very setup dependent. And so, yeah, I think we'd have to like sit down, and I think Ethan and I would be happy to do that at some point in time if you want, Miles. But yeah, that could be it. There could be, if you're measuring force and length through different devices, there could be different latencies or synchronization through that. We've had to face that issue before. You can do all these work loops in vivo with like sonomicrometry and tendon buckles. Monica is like the expert on that. And so like, you know, you can measure these things in different ways, but then you do have to be really careful about, you know, whether the measurements are lined up in time and whether you're taking an equivalent length measurement to the force measurement that you're intending to. And so like for a muscle tendon unit, you could do a work loop on the muscle tendon unit or on the muscle itself. And people have done both of those. And actually, Jill, to go back to your question, that was sort of the kind of thing that we're doing here. It's sort of like the muscle exoskeleton is sort of like a muscle with a parallel tendon as opposed to a series tendon. And so we can look at those two components and decompose them just like you would the contribution of a tendon and the contribution of a muscle. And I'll also just say like work loops are actually where they really are just stress strain or force length curves. People do this all the time to characterize like a spring or other passive elements. It's just with a passive element, you can't do net positive work because there's no internal energy supply, right? There's no way to do positive work. And so muscles are things that can have activated stress strain curves that have positive work. But you can do a tendon and you can do a force length curve. And that's technically what we call a work loop, is really in the materials literature or what in the physics community of what's called rheology, so the material properties of soft things. That's just called a stress strain curve through a cycle. And so it's useful to know that those terms are sort of used similarly through that.
But yeah,
but yeah, Miles, I think we should, yeah, send up. Let's look at the details. And
thanks.
Anything else, folks? All right. Next IMSI workshop is Thursday, right?
Thursday, and I think Christian, you're still on for Thursday? Is he still in the call?
I think Christian is not still on, but he's hopefully still on for Thursday.
Yes, he's still on for Thursday. So thanks, everyone. We'll sign off for today. And thanks again to Ethan for the live demo. That's awesome. And Simon for your really clear explanations. It's really good to go back to basics and review all of the fundamental principles. So thanks for that. And we'll see you all on Thursday. Oh, mentoring workshop tomorrow. Remember that too, 9 a.m. All right.
Thanks all.
Yeah.